Hello everyone, welcome back. In our last lecture, we established that cache memory is a small, high-speed component designed to hold copies of data from the massive main memory. However, this difference in size creates a fundamental operational problem. Imagine your main memory is a massive library with 16 million books, but your cache, it's a tiny backpack that can only hold 1024 books. Here is the million-dollar question. When you bring a book from the library, where exactly do you put it in the backpack? Do you just throw it in randomly? Do you have a specific pocket for it? This set of rules is called cache mapping. It answers the simple question, where can a specific block go? To answer this, the hardware doesn't guess. It looks at the memory address. Think of the address like a postal code. We split it into three parts to navigate. Offset, this finds the specific byte, like the page number. Though we don't care about this for mapping. Index, this is the most important one today. It decides which line or pocket we look in. Tag, this is the ID card. It verifies if the data we found is actually what we wanted. The entire difference between the three mapping techniques is how the tag and index fields are defined. Now, before we look at the solutions, we have to understand the problem. You might ask, why do we have three different complicated ways to map memory? Why not just use the simplest one? The answer is simple. Different mapping techniques are good at fighting different types of failures. We call these failures the 3 C's. If you don't understand these, you can't understand why modern CPUs are designed the way they are. First is the compulsory miss, often called a cold miss. This happens the very first time you access a block. It has never been in the cache before, so you must go to main memory to get it. In reality, no mapping technique can fix this. It is unavoidable unless you have a psychic computer that prefetches data before you ask for it. Second is the capacity miss. This is purely a size issue. Your program is using more data than the cache can hold. To bring new data in, you have to kick old data out. In reality, mapping doesn't really fix this either. The only cure here is to buy a bigger cache. And finally, the reason we are here today, the conflict miss. This happens when the cache is not full, but two specific blocks are fighting for the same specific seat. One kicks the other out, over and over again. Why do you need to know this? Because the entire goal of the mapping techniques we are about to learn is to eliminate this specific enemy. Direct mapping fails here. Fully associative solves it. Set-Associative balances it. We design mapping rules specifically to stop these conflict misses from destroying your performance. Alright, let's start with the first technique. This is the simplest, the cheapest, and the fastest to build. It is called direct mapping. The philosophy here is strict. I call it assigned seating. The rule is simple. A specific block from main memory has only one specific place it can go in the cache. It doesn't get a choice. The index is rigidly defined. But how does the hardware know which seat to assign? It uses simple modular arithmetic. The formula is cache line index is equal to block address modulo total cache lines. Now, let's look at the address split. This is crucial. Because the destination is fixed, we use a specific chunk of the address called the index to point us directly to the line. If your cache has 1024 lines, because 2 to the power 10 is equal to 1024, the hardware grabs 10 bits from the address and, for example, says, go to line 5. It's instant. There is no searching. It's like a GPS coordinate. Now, just quickly see the lookup process. When the CPU requests a memory address, the hardware takes the 10 bits index from the address. Then, it goes directly to that single line in the cache, which is calculated by the formula we've just seen. Then, it checks the valid bit. If it's 0, it's a cache miss, and if 1, it compares the tag bits from the address with the tag stored in that line. Finally, if they match, it's cache hit. And if they don't, it's cache miss. To understand why the direct mapping is both good and bad, imagine a university exam hall. You are a student, and based on your student ID, you are assigned a specific desk number 5. The rule is strict. You must sit at desk 5. It doesn't matter if desk 6 is empty. It doesn't matter if the entire hall is empty. You have to sit at desk 5. Now, The good news or the advantage is that this is incredibly fast. You don't walk around looking for a seat. You walk in, look at your ID, and sit down. Zero wasted time. In direct mapping, the hardware implementation is simple, straightforward, and cheap, consisting only of an array. And also, no search operation is necessary. The lookup is immediate and direct. But what happens if another student arrives and he is technically assigned the same desk too? He will kick you out, and then you will kick him out to get the seat. This constant fighting over the same seat keeps going on. Now, this is the disadvantage here. Look carefully. This is the conflict misses, which we talked earlier, and this is the fatal flaw of direct mapping, which causes thrashing. Thrashing is a performance degrading cycle that occurs in a direct mapped cache when two or more memory blocks repeatedly compete for the same single cache line. This constant conflict causes the blocks to be repeatedly loaded into the cache, only to be immediately evicted by the other block when it is needed next. Imagine the CPU needs block 5 and 1029 at the same time. If the cache has 1024 lines, 5 mod 1024 is equal to 5, as well as 1029 mod 1024 is equal to 5. So block 5 and block 1029 both map to the same cache line, 5. Now, block 5 is loaded, which is a hit. Then block 1029 is needed, so it evicts block 5, which is a miss. Again, block 5 is needed, so it evicts block 1029, which again is a miss. This continuous cycle of evictions and subsequent misses is thrashing, which severely compromises system performance because the CPU spends excessive time fetching data from main memory instead of executing instructions. It is the main weakness of direct mapping. So, we just saw that direct mapping is fast but rigid. It causes thrashing because of those strict seating rules. So, let's go to the extreme opposite. Let's remove all the rules. This is fully associative mapping. The philosophy here is total freedom. The rule is that a memory block can go into any empty available line in the entire cache. If slot 1 is full, put it in slot 2. If slot 2 is full, put it in slot 100. As long as there is space, come on in. But wait, if data can be anywhere, how do we find it? In direct mapping, we had an index, a map that told us exactly where to look. Here, we have no index. The address is just a massive tag and an offset. This creates a massive hardware challenge. Since the data could be in line 1, line 50, or line 500, the hardware must check every single line in the cache at the exact same moment to see if the tag matches. It can't check them one by one, that would be too slow. It has to be a parallel search. To do this, we use very special, very expensive hardware called CAM content, addressable memory. This isn't normal memory. It's memory that can search itself. Think of this like a messy desk. You have a piece of paper and you can place your paper anywhere on your desk. Here the advantage is you never have a conflict. There are no restrictions, no pre-assigned sections. If there's an empty spot, you can use it. There's no chance of being blocked by an already occupied preferred spot. But the disadvantage is that when you need to find that paper later, then good luck, as you have no idea where it is. You have to scan the entire desk parallelly to find it. And as I said just now, parallel comparison necessitates the use of specialized, complex hardware known as content addressable memory. And here, comparing every single tag in parallel requires millions of comparator circuits. CAM is expensive as it takes up too much physical space on the silicon chip. CAM exhibits significantly slower operating speeds and greater power consumption compared to standard synchronous RAM. Because of this, fully associative mapping is not scalable. We only use it for very tiny, specific caches like a TLB, but never for a massive 4 megabytes or 8 megabytes cache. It's just physically impossible. So now we have direct mapping, which is too rigid, and fully associative mapping, which is too expensive. We need a middle ground. We need the balanced solution. So, till now, we have seen the two extremes. So, engineers asked, can we have the speed of direct mapping, but the flexibility of fully associative? The answer is yes. and it is called n-way set-associative mapping. This is the standard used in almost all modern CPUs like the Intel Core or AMD Ryzen inside your laptop right now. Here is the genius idea. Instead of mapping to a single line, we map to a set of lines. Think of the cache as being divided into groups. If we have a 4-way set-associative cache, it means every set has 4 available slots or ways. The rule is that a memory block maps to one specific set, but once it gets there, it can take any of the 4 available seats inside that set. Now, how do we find the right set? We use the modulo operator again, but this time on the sets, not the lines. Cache set index is equal to main memory block address mod s, where s is the total number of sets in the cache. Now, look at how the hardware slices the address. This is the perfect hybrid. Here, offset still finds the byte, and here, set index is smaller than the direct mapping index. It points us to the specific set and tag checks if the block is actually the one we want. Let's crunch the numbers for a real example. A 1024 line cache that is 4-way set associative. Here, we simply take the total lines and divide by the ways. So, 1024 lines divided by 4 gives us exactly 256 sets. To find one of those 256 sets, we take the logarithm base 2 of 256, which equals 8 bitses for the index. For the offset, assuming a 64-byte block, we need 6 bitses. And the tag, it simply gets whatever bits are left over. Now, let's see the lookup process quickly. The CPU requests a memory address. So, the hardware takes the set index bits and it goes directly to that set. It then performs a small 4-way parallel search, comparing the tag from the address against the 4 tags stored in that set. If any of the 4 tags match and are valid, then cache hit. If none match, then cache miss. Now, to make this stick, let's use the movie theater analogy. Your ticket, which is the memory address, assigns you to a specific row, which is a set. The rule is strict. You must sit in row 5. However, once you get to row 5, there are 4 empty seats. You can sit in any of those 4 seats. Why does this solve the problem? Remember block 5 and block 1029? They were fighting over the same seat. Here, they both go to row 5. But block 5 takes seat A, and block 1029 takes seat B. They can coexist. No thrashing. Finally, the biggest realization moment. Don't think of these as 3 different techniques. Think of it as a slider. Direct mapping is just a one-way set associative cache where there is one line per set, resulting in 1024 sets, rigid and fast. On the other hand, fully associative is just a 1024-way set associative cache where there are 1024 lines per set, resulting in a single giant set, flexible and expensive. And in the middle, there is 4-way or 8-way. This is where modern engineering lives, balancing speed, cost, and performance. Finally, just check out this comparison table. Everything is summarized here, which we've talked about. So let's wrap this up. So let's bring this all home. Today, we didn't just learn about organizing memory. We learned the fundamental lesson of engineering, the art of compromise. Now, why does this matter to the world? I want you to look at the phone in your pocket or the laptop on your desk. Have you ever wondered why modern processors like the Apple Silicon or the Snapdragon in your phone are so magical? Why can they play high-end games but still give you 18 hours of battery life? The answer hides in the associativity we just discussed. Think about it. If your phone used fully associative mapping for its massive caches, every time you open Instagram or YouTube, the hardware would have to fire millions of comparator circuits to search the entire cache for data. Result? Your phone would get incredibly hot in seconds, and your battery would die in an hour. That parallel search burns electricity. But by using set associative, specifically 8-way or 16-way, engineers found a way to search only a tiny corner of the memory. They save microscopic amounts of energy on every single click. But when you multiply that by billions of clicks a day, that specific mapping decision is the reason we have mobile devices that last all day long. And let's look even bigger. Think of the massive data centers that power the internet, AI, and cloud computing. These places consume massive amounts of electricity. When engineers design the server CPUs, like Intel Xeons or AMD EPYCs, they choose the mapping technique carefully. If they choose the wrong associativity and the hit rate drops by even 1%, those servers have to wake up the main memory more often. That costs power. By optimizing these mapping rules to maximize hits and minimize power, engineers aren't just making computers faster, they're actually reducing the global carbon footprint of the internet. That is the power of what you are studying. You aren't just moving bits around. You are learning the logic that makes the digital world efficient, sustainable, and powerful. Now, we have one final mystery left. When the cache is full and we must bring in a new block, who gets kicked out? Do we kick out the oldest one? The least used one? That is the battle of replacement policies, and we will decide the winner in the next video. I'll see you there.